Hello, everyone. So, what I wanted to do here was to put together a few videos for some of the formulas that we are going to use during AC theory, and hopefully you find these helpful. My name's Jason Doty. Most of you will know me from sitting in my classroom. Uh, And the first video we have here for you guys is on inductance and inductive reactant. Hope you enjoy it. Any of your feedback would appreciate. Leave a comment. And if there's something that you want to see, let us know. Welcome, welcome, welcome. So we are going to talk about the difference between inductance and inductive reactance. Two different units of measures when we talk about our inductors. One is going to give us the value of an inductor in henries, the measurement for inductance. The other formula we're going to take a look at today is a formula that we use quite often in our AC theory calculations, inductive reactance. We're going to take those henries and we're going to turn them into something we can use to make electrical calculations. Inductive reactance measured in ohms. So first, let's take a look at our inductance formula. L stands for inductance measured in Henry, equal to 3.19 times the number of turns squared times the area of the core material, whether that's an air core, iron core, other material, and of course for mu, which stands for, in this formula, permeability of the core material. All of that divided by 10 to the 8th times the length of the core. So this is really helpful when we have to decide what factors go into inductance. So again, we'll go through a couple of these variables and give their meaning, right? The n squared. Again, number of turns in the wire. That's all an inductor is. It's a coil of wire with an iron core, an air core, some core material. So we now know what N stands for. The A. This is going to be the area of the core material. Right? And we all know area is length times width. That's what we're looking for there. Of course, our mu, which is the permeability of the core. Air has a certain permeability from a permeability chart. Iron, the most common core of an inductor, has better permeability. And permeability really is just the ability to organize the molecules in the core material. Finally, we use a lot of L's here. So we go with the cursive one. That'll be the length of the core. This will all result in the value known as Henry. The value we measure inductance in. And Henry's is really what we're looking for so that we can now make electrical calculations. Henry's doesn't help us much, but we're going to look at another formula called inductive reactance here, where we're going to turn those Henrys into something we can use. Okay, so let's get rid of this. And let's take a look at the inductive reactance formula. Inductive reactance is expressed by XL. And again, we're going to measure this in ohms. Henrys ohms. And the inductive reactance formula is a little bit simpler than the inductance formula. It is 2 times pi. And when we use pi, we're always going to use 3.14. Now, there's plenty of people out there that can sit there and tell you that pi is infinite in the decimal, and they can probably name about 15 of those decimal points, and that's fantastic. But for our purposes, for what we're going to try to accomplish here, we're always going to use 3.14. So when you do this calculation, don't use the pi on your calculator. Use the value 3.14. And then we have F, and of course, L. L, as we know, is the Henrys from our inductance formula. So what's the F, you ask? Yet more answers we can get when someone asks us a question, well, what factors go into inductive reactance? Truly only 2. The Henrys, of course, and the F here stands for frequency. Frequency of the AC sine wave. Here in the United States, of course, we know it's 60 hertz. Europe, you'll use 50 hertz. And they all have an impact on inductive reactance. The other thing it tells us is that in a DC circuit with a coil or an inductor, there is no inductive reactance. Because in a DC circuit, we don't have frequency. It's all or nothing when it comes to power. Much, much different when we're talking about AC sine waves here. So now we have all the factors that go into both of our formulas here. And again, just a short kind of video here to give you a little bit more understanding of what the variables are in these equations, how we're going to apply them. And so let's jump into the inductive reactance formula, because as an electrician, that's the one I really care about. I can't do much with Henrys, so if I had a 2 Henry inductor, I need to figure out how voltage and current are going to act, because it's going to be in opposition to that current flow. We know resistors are opposition to current flow. Now we're getting introduced to another form of opposition to current flow in inductive reactance. Can't do much with Henrys, so let's see what we can do here. What we're going to do is take 2, multiply that by 3.14, multiply that by the frequency. We'll use the one that we typically have here in the United States, 60 hertz, and the 2 Henrys from our inductance formula. What we have determined that inductor will give us in Henrys. So if we take those numbers, we plug them into our calculator, straight multiplication, so nothing goofy going on a calculator, we will get a result of 753.6 ohms. 753.6 ohms for a 2 Henry inductor at 60 hertz. This is where we can kind of play around with this stuff. Say we, for whatever reason, increase the frequency. We're not at 60 hertz anymore, right? This was our 60. We're at 120 hertz. Well, I'm sure that some of you figured this out. That probably doubles that number of 753.6. Well, let's find out. Let's prove it, right? 2 times 3.14 times 120 times 2. And look at that. You were all absolutely right. This inductor at that frequency, the 1,507.2 ohms. And really what we have to concentrate on here is the ohms. Because now we can use that value when we know an applied voltage to figure out an applied current, to figure out total power, multitude of our electrical calculations we remember from EC theory. Hopefully this little video here will help you understand the difference between inductance and inductive reactance, why we have these formulas, what our variables mean, and how we're going to use them to really get to what we need, which is ohms. Thanks, everybody. Thanks for what you do for the electrical industry, and we'll talk again real soon.